We move to an approach to achieve compositional generalization. We mainly discuss how to encode the prior knowledge and enable conditional independence property. Let's look at a compositional generalization problem. There can be many settings for compositional generalization, and we discuss a general one. We consider the problem has both entangled input and entangled output, and the components are aligned. For example, in language translation, both input and output languages are entangled with grammar and lexicon. The input grammar decides output grammar, and input lexicon decides output lexicon. A conceptually straightforward way to address the problem is to use disentangled representation. We do not assume statistical independence between components or use annotations on components. In such setting, the network can be separated to encoding and decoding. Encoding converts entangled input to hidden representation, and decoding converts the hidden disentangled representation to entangled output. We can use the same input and output for representation learning. We hope a component representation HI has exact information of the component with prior knowledge. For example, we hope a component contains the information of color. This means we need to control information of a random variable. Let's think about an analogy of how to physically fix an object at a position in the air. A simple way to do this is to move the hand below the position and put the object on the hand. The object is kept stable at the position because there are two balanced forces. One force is local, strong electromagnetic force from the hand to the object pointing upward. This is local because when the object does not contact the hand, the force disappears. And it is strong because even a small change of hand shape produces strong force. Another force is global and weak gravity. These two forces are equal in magnitude and opposite in direction to fix the project. When we look at the potential energy, it means the energy minimum is at the fixed point. So please refer to the intuitive plots. The advantage of this approach to fix an object are the following. First, the target position is encoded only into one force. This means we do not need to manipulate gravity to have some special value at the target position. Second, it does not need specific values for the forces, as long as one force is local and strong and the other is global and weak. This means we do not need a scale to get the gravity or measure the force of hand shape change. Similar techniques are available in machine learning, and we are going to discuss them. In machine learning, the analogy is that the position is the information of a component representation, and the potential energy is the optimization loss. Entropy is the amount of information of the representation in a distribution, and we use it as information for explanation purpose. We use optimization to find the minimum loss. We then look at what techniques we have for the forces. The upward force to increase entropy is prediction loss. When we train a model to have correct prediction, an intermediate representation should contain more information to do that. The locality can be achieved by architecture design, as we will discuss later. The downward force to reduce entropy can be achieved by regularization, and we also discuss later. However, it is not clear how to reduce entropy locally at a specific point. With this availability of techniques, we use prediction laws and architecture design for upward local force and regularization for downward global force. Let's discuss the techniques. We will first discuss how to encode the locality when increasing information. This means that we hope to make a component representation has at least certain information. We achieve this by architecture design combined with prediction laws. When an output component yi is connected only with one hidden component representation, then its information can come only from this hidden component representation. Since this component needs to be correct when reducing prediction loss, the hidden component representation should contain at least the information of the component. We will look at an example in the next slide. Note that this technique works for the decoding process because the output needs to be compared with ground truth to compute the loss. Also, for humans, describing the decoding process is easier than encoding process. For example, computer graphics is easier than computer vision. Computer graphics in many cases do not need machine learning, such as developing 3D games. However, computer vision is hard without machine learning. So this is the way that we encode component prior knowledge in the architecture design. And please find more information in this paper. Let's look at an example. There are two component representations, one for shape and the other for color. We can design architecture to achieve the following effect. The shape in the output changes only when the first component representation changes its value. The color of the output changes only when the second component representation changes its value. To make the output as expected, the first component representation should at least contain the shape information, and the second component representation should at least contain the color information, because the other representation is not able to change the information in output. We then talk about reducing the information in a component representation. This does not require component-specific prior knowledge. Entropy for a random variable can be roughly understood as the number of possible values. We can reduce the entropy of a representation by adding noise and reduce the norm of the representation. The noise makes different values far from each other in vector space. If they are close, the noise will make them not distinguishable, so the prediction will be wrong. At the same time, norm regularization will make different values close to each other to reduce the region of manifold. These two forces scratch the values so that unnecessary values will be merged to the same value. With this number of possible values, the entropy reduces. I'd like to share a joke of law of entropy increase in human language learning. Law of entropy increase is originally a law in thermodynamics for physics. It says in an isolated system, the entropy increases over time. Here, as a beginner of learning a second language, one is likely to overuse compositionality to create natural phrases. As one becomes more fluent over time, the problem is less. Um, we discussed two forces to increase and decrease entropy. However, during the optimization of neural networks, there are other forces, and we need to consider all of them to find the balance point. The other forces come from stochastic gradient descent. It is a widely used optimization algorithm, and it has many variations, but the following arguments apply to them. One force comes from gradient descent. It increases entropy of a representation. This mainly happens during the early stage of training. This force makes entropy realization important to cancel this force. I will discuss it in the next slide. Another force is from stochastic sampling. This reduces entropy because it adds noise. The effect is similar to entropy visualization, but this is weak. This effect appears mainly during the later stage of training. So occasionally, this enables learning compositionality without entropy visualization. For more details, please refer to this paper. Let's talk about why gradient descent increases entropy. This is because optimization process imposes a bias towards non-compositional solutions. And this is caused because gradient seeks the steepest direction so that it uses all available and redundant input information. So this increases information of component representations. Illustratively, theta A is compositional and theta B is non-compositional solutions. Then in the parameter space, the gradient encourages parameters closer to B, theta B. Please refer to this paper for more details. Let's summarize the four forces. The first is from prediction loss with architecture design. This force is high when entropy is small, and it disappears after the entropy is above the target value. The second force is from stochastic sampling. This force exists naturally, but is weak. The third force is from gradient descent. This force increases entropy, which makes the prediction loss is not enough to achieve the expected target value. The fourth force is entropy generalization that counteracts the force from the gradient descent. This force should be greater than the one from prediction loss so that the entropy has the lowest point near to the expected target value.